what does the question say? The question says that there is uniform. Now that means it is constant with respect to coordinate, right? Magnetic field in cylindrical region of radius capital R varies with time as this. So the magnetic field undoubtedly is uniform, but it is not steady because it's varying with respect to time. So uniform means constant with respect to position, while steady means constant with respect to time. So it's a clear case of time varying magnetic field, and with a little bit of preparation this concept will auto strike that hey, now it has to be linked to induced electric field. Now alpha is a constant and there is a conducting rod AB of length root 3r. Okay, so here is that particular rod of length root 3r, and I need to calculate the induced EMF across ends A and B. Now if I go through the first method, which is completely going through the basic, that you would see the electric field induced is in the form of concentric rings of increasing radius, and you would use the formula to calculate the electric field. You would suitably integrate it to calculate the EMF, but that's not recommended. If you just see these category of question, if you use a proper idea of symmetry, you can do with certain amount of ease. So let's see how it goes. Let's see how it goes. Look, here is this situation. Now you can just see right here. This is root 3r, this is radius r. So how much would be this particular angle? Well, that's 60 degree. So I would write it as pi by 3. Similarly, this angle, that's pi by 3, isn't it? Because this is radius, so you can use the t ratio and you can see. Now, do you realize that this rod is subtending an angle of 120 degree with respect to the center? It means we can go with the idea of symmetry and say that if I go for some additional construction, so I have added two identical rods in a very symmetrical manner so as to complete the equilateral triangle. Now, can you find the induced EMF across this imaginary loop whose circumference or whose perimeter is this triangle? I think perimeter would be a better word, isn't it? So this is that loop. I'll find the EMF, then what? Now realize, because this is a very symmetric figure, the EMF induced would be equally divided amongst each rod. So I think that would be a better idea. So first of all, we need to calculate how much is the area enclosed by this triangle. Now that would be 1/2 of base, which is root 3r, isn't it? And height. So this is that height. This angle is of course how much? 60 degree, which is pi by 3. So that's going to be root 3r sine 60 further, so root 3 by 2. So I calculated the area enclosed by this figure. Once I get the area, I can now calculate the flux, which would be equals to B multiplied by A, and the EMF magnitude, if I see, that's going to be d phi by dt. Okay. Now once you get the EMF, that EMF is across all the sides, in other words, in the entire perimeter of the triangle. But the question demands us to calculate the EMF across this segment. So all you need to do is that you need to divide the EMF by a factor of 3, and that is going to give you option number C as the correct one. Let's go for the next. Okay. Current electricity. Now, in a first glance, it seems to be very simple. Now, it tempts you to say that, hey, this is the Wheatstone, but remember, the values are shifted. So it's not a balanced Wheatstone, but even within this unsymmetry, there is a pattern. And do you see 4 2 2, 4. And what's the question? I need to compute the current through 1 ohm. Now, let me just try to share a method which I personally like in order to solve the shifted Wheatstone. Because see, the logic, the symmetry of the problem is whatever current passes through 4 ohm here, the current through this would also be same. The current through this 2 ohm and this 2 ohm, that would be same, right? So that can be argued by symmetry. So one way is that you go with KVL, but there is another way which is even much convenient than KVL. Let's see how. If I say this potential as 0, I assumed it. So this is also going to be 0, this is also going to be 0. Now how much will this be? That's going to be 20. So you start it here, this is 20, this is 20, you get that point. That's how it goes. Cool. Now after that, I don't know the potential of this point, but let me say that the potential of this junction is V. Now here, one option is you write as V dash, but just think, if you write it as V dash, you would have altogether 2 unknowns, and for 2 unknowns you will be requiring 2 equations. But if you understand the symmetry of the situation, you would see, if we go a bit technically, you need to solve only 1 equation, and you would say, hey, that's a wanted feature, because lesser number of equation, the hassle is less. Now what technique and what skill can I use? What is the potential difference across this 4 ohm? 20 minus V. So the potential difference across this should also be 20 minus V, because the resistance is same, the current is same, which implies the potential difference must be same. So there you have already written as 0, and you know the potential difference must be 20 minus V. So it gives us no option but to write the potential here as 20 minus V, so that the current through this and this, that would be same. Now the whole focus would be, how are we going to calculate the value of V? For that, I need to see one junction. So I assume the current direction as this. It's purely an assumption. Now as per the KCL, not the potassium chloride, Kirchhoff's current law, the incoming current has to be equals to outgoing one. So what would be the incoming current? So that's going to be 20 minus of V divided by 4 is the current here, and the outgoing is the current through this 1 ohm. So that is going to be V minus of 20 minus V divided by the resistance is 1, and this current, so that is going to be plus V minus 0 divided by 2. So what did I do? Essentially, I have written incoming current equals to outgoing, and this is an easy equation you can solve for V. But then you would say the question had asked about the current through 1 ohm. Now is it a difficult issue? I don't think so. It's not at all a difficult issue, because the potential difference divided by the resistance is going to give you the current. So that much part I expect from you. So you solve that. That's going to give you option number C as the correct one. All right, so here is the 6th question, and this is the final question of this segment, not of the paper. Okay, so after this we are going to handle the multiple correct option. Now the question is from Doppler's effect. There is a passenger standing on the railway platform. Observe that as a train passed this station at a speed of 90 km per hour. So that means that's going to give how much? 5 by 18 if you multiply, 25 meter per second. So I can just start writing this, that the velocity of the train, that is equals to 25 meter per second. The apparent frequency of the whistle, appear to drop by 400 Hz. Now, why does this happen? Initially, the train is approaching, so the frequency is higher, and after that the train recedes, so the frequency would be lesser. So, there is a drop in frequency, and how much is that? That is 400 Hz. Now, on the basis of this data, we got to calculate the actual frequency of the whistle. So, I do not think so there is a challenge at all in solving this. All the parameter has been given. Now, you see initially how much was the apparent frequency? That was the real frequency V upon V minus Vt. This is a case of source moving, detector at rest. And later on when the train recedes, so that is going to be V divided by V plus of Vt. So, one is the higher frequency, other is the lower frequency, you subtract it and you equate it to 400 as per the question. So, it is purely a little bit of arithmetic. So, when you solve that, you know one more thing, the options are very widely spread. So, you may not require to solve in the entire accuracy. After 3 or 4 steps, you would soon guess that option number C is going to be the correct one. Alright, so that was the end of the first variety, single option. Now, it is time we go for the next one.